Good afternoon. Welcome to the training, the OpenGadget code for cosmological simulations, which is delivered to you under the auspices of Project Space, which is Center of Excellence for HPC Astrophysical Applications. Today, we are going to introduce to you OpenGadget code. This training is addressed to HPC experts from all domains interested in evolving their codes to exa-scale. The audience, you will benefit from the training, discovering how a different community is solving computational problems and implementing algorithms. And our tutors will obviously be very happy if you share your observations, discussions, suggestions, or even if you spot an error. And our tutors today, or the people who prepared this presentation for you, are Luca Tornatore from Italian National Institute for Astrophysics and Geray Karademir from Ludwig Maximilians University in Munich, Germany. They are both astrophysicists and cosmologists, and they conduct their research activity mainly using numerical simulations as tools to inquire about the intricate web of physical processes that shape our universe, from large scales down to galactic scales. And they also became HPC experts, and as such, and they experienced a cumbersome double personality. So, Geray, the floor is yours.
Thanks for the introduction. So as Karina already mentioned here, my name is Geray Karademir. I'm a researcher at the Ludwig Maximilians University in Munich, and I'm now going to present to you and show you a little bit about insights into the OpenGadget code. And please feel free to ask any questions afterwards. But before we get started into the technical details of the code, first of all, maybe as a reminder, let's say, why are we even doing all of this? So in case some of you are fortunate at some point, have some spare time, or live on a remote place somewhere, I can only recommend looking up in the sky once in a while. And if you're even more lucky and don't have rain all the time, which we had here in Munich the last few months quite a lot, you are able to see the magnificent night sky, which we are blessed with here on Earth. And you can see, even as you can see here in this image, of course, this is kind of like the perfect which you could get in theory. And you will see that there are millions and millions of stars, which you're just able to see by simply with your eyes. But that's not all. So if we use all the telescopes and the instruments which we have available by now, and all the research which have been done in the past, we have realized that there's so much more than just the stars we can see with our eyes. So there are even more larger objects around, like galaxies, which you can see here on the left in this image, which is like a beautiful spiral galaxy. And you can see already this is not a simple object. It's highly complex. It has spiral arms. It's interacting with this other galaxy or object up there. You can see these weird streams and things going around. So very, really beautiful already, but very, very complex as well. Then if you look at a little smaller scales, like here in the middle, you will see these beautiful nebulas, so kind of like gas clouds, in which stars are born, or stars are forming. And you can see in there the newly born stars, but you can also see the shock fronts in the gas and all these different parts, processes going on there as well. And if you go on even smaller scales, a few years ago, we were finally able to get a picture of a black hole. Actually, this is really impressive to me as well that this actually worked. And so there are also objects which are really, really small, very, very obscure in any way, and which are very, very different to what we think or what we experience from our daily lives. So there's not just stars. There's so much more in the universe which we know already and which we want to deal with. And as already gives you a hint of what kind of complexity we're working with. So if you just look at the different star galaxies and so on, this is a huge range of scales. So you have an objects which are maybe even, up to star-sized. You go up to hundreds, billions of stars which form a galaxy, but there's even more. That's a universe in general. And here in this image, there's kind of like shown to you what we know about the formation of the universe in general. So you're starting from the Big Bang up to today. And what we want to deal with is exactly, we want to look at the evolution and we want to learn from it. And you can see this is not just large scale difference from beginning to the end, but also the time changes quite a lot. So there's a huge amount of time. We're talking about 13 billion years from, let's say, the era of free combination. So the first time when the universe that we can see the universe in that sense. When we started when this first kind of like objects formed, so just dark matter which clustered, until the first stars finally appeared, and then until modern times where you get these beautiful galaxies and the clustering of matter, and you see the big differences in what happened in these 13 billion years. It's not just stars evolved, but also the universe developed from a very homogeneous state up to the clustered state which we have right now. And we want to learn something about this process. And our tool and what we do are so-called cosmological simulations. And that's what we are doing, we're aiming for. What's the purpose of OpenGadget? So the purpose and the aim is we want to learn about the formation of large-scale structure. We want to learn how galaxies form, how they evolve. We want to learn about the gas, how the dynamics within, how they form stars, how their feedback, of course, then affects the gas again, how black holes and their feedback affects galaxies, how do magnetic fields, what kind of role do they play within this whole evolution process, and so many more processes which are underneath. And for all of this, we use cosmological simulations. And one of them you can see there on the right. This is a snapshot or an image of the Magneticum Pathfinder simulations, where we create these boxes, how we call cosmological boxes, how we call them. So we try to simulate the universe in a certain shape, in a certain size. And then we kind of like zoom into that box and trying to find all the objects we're interested in. And as you can see here very nicely, you have this beautiful box with all the cosmic webs, all these nodes and filaments going for everywhere. And you have the galaxies and the clusters sitting at the nodes of these filaments or along these filaments, or sometimes even in the voids in between. And then we look at these objects and we try to learn something about it. So that's kind of like the purpose, and that's what we want to achieve with OpenGadget. Of course, calculating all of this is a challenge, definitely, especially if you want to go into details, because there's so many processes involved, and there's so many members or particles, how we call it, in that simulation. As you know, there are so many stars, and therefore there must be a lot of particles as well. I'm now going to describe you one of the main challenges, and there are a lot of other algorithms involved as well, but half an hour, unfortunately, isn't enough to describe the whole code and its all complexity. But one of the main challenges, and that's for this kind of realm, that's simply how do you calculate gravity effectively? I mean, we all know from school how gravity is calculated in general. We know this since a few hundred years, but this scales as n squared with the number of particles, because you have to always consider the force between 2 points all the time and between all of them. So you always have to calculate the forces which are interact and which then leading to the interaction between the different particles. Now this is very computationally heavy. Here on the left, you see a plot where it's the number of particles versus the year a simulation has been done, and you can see that this direct approach of calculating gravity doesn't allow for a large or huge number of particles. So the gravity or the direct summation simulations are the green, blue dots you see there at the bottom. And you can see that they are lacking in the number of particles you're able to process with them, because the computational cost associated is just too extreme to be dealt with, except of course you have unlimited computational power, but unfortunately that's simply not the case. So you need to find different algorithms to calculate gravity effectively, but also accurately. And they are, like, I would say, two different ways in addition to direct summation. These are so-called grid approaches, where you grid your particles in a certain manner and you then calculate the forces according to the grid, which is one approach. The other one, or a second one, is then a tree approach, where you group your particles by a hierarchical tree, and then you get the connections and assign which particles are close to each other, and so on and so forth. And with that, you're able to process a significant fraction of more particles with the same computational cost compared to direct summation. And this, of course, allows us to get more details about the universe and about everything, because this way we are able to create larger boxes with more objects, more details, higher resolution, and so on and so forth. So this is very important for us, that the calculation of gravity is done effectively. In OpenGadget, we kind of like approach a three-stepped scheme. So on the very, very small scales, we actually do calculate the gravity pairwise directly by direct summation. This is simply because this is the only way of doing it as accurate as you can. And objects which are very close, or particles which are close to each other, they have also the highest, there the error would matter the most. If you do something wrong there, because they are closest, their forces are the largest, and so on. So in small scales, we do it really via direct summation. But on intermediate ranges, we opted for a different algorithm. And this algorithm is a so-called Barnes and Hut-Ock tree algorithm. So what we do here, we split all particles, so our volume, into small cubicles with particles, and we do that recursively until at the end we have one particle per box, let's say. So you can see this here in this image very nicely. So you have this in 2D, of course, here for simplification. You have a certain number of particles within a certain volume or area here, and you split that by always splitting each region, each node into 4 sub-regions until you only have one particle per region. And this way, it's much easier to calculate and much faster to calculate long-distance forces compared to direct summation, because you then kind of like can group particles which are within a larger or higher level node and then you don't have to calculate the forces pairwise, so you can, which saves you, of course, a lot of interactions, a lot of time. If you then go to even larger scales, we even implemented a particle mesh grid in addition to that. So you kind of like have all 3 different ways of calculating gravity all in the same code. So on top of that, of the tree, which is for intermediate ranges, you have a mesh grid as well. And there you just assign your particle to the mesh, and you calculate the contributions to each mesh cell by the particle, and then calculate the forces in between the different cells. The advantages of this is, of course, it's very, very fast and very easy to implement. The downside is that the resolution, the accuracy is significantly lower compared to the first 2 approaches. So we only use this for the really large distance forces, where small uncertainties are not so important. But having a lot of particles and, aiming to scale on large machines, we have to distribute the workload somehow, because this can't be done in a serial job anymore, unfortunately. Since the number of particles is quite large, and in theory, every particle needs to know all information about all other particles all the time, because they're all interacting all the time with each other via gravity, the code is in general very memory limited. So, but we have to find a way how to break this kind of like degeneracy here. And we do that by splitting our computational volume using a domain decomposition based on a Peano-Hilbert curve. So what we do here, we use a space-filling curve by which particles which are close in real space are connected also in a way so that they're also at the end close in memory. And therefore, of course, this is very beneficial, because the closer they are in real space, the more they interact with each other. And therefore, it's very beneficial, of course, if they're close in memory, because otherwise, this way you save a lot of communication. And in the end, the idea is behind building this space-filling curve, you then create chunks of it and then send them to the different MPI tasks. And then every MPI task is working on this chunk and then only distributing the information which it still needs across the boundaries of these different chunks. But how do you build this curve? So what is the workload in general? This is also an interesting question, which increases the complexity of this domain decomposition, because it's not just a number of objects. It's not like every particle requires the same amount of computational effort. it really depends on where the particle is. Is it in a highly homogeneous area? Is it in an underdense, or is it really in a dense environment where it has a lot of very close neighbors? So of course, if it's in a very dense environment, a lot of close neighbors, the computational cost associated with the particle is much higher than to a particle which is in the underdense region, where the distances to the next particle are much larger. And this you can see here in this image down here as well. So if you would split this sphere of particles just by the number of particles, you would create something like the second image on the left. But this is not the real workload associated. So what we do, we kind of like combine, we try to keep similar number of particles because of memory reasons within each block, but also try to keep the workload associated to them in a roughly, of course, it's not perfect, but in a similar manner. Because this way we can then avoid that the different MPI tasks finish at different times, so that all are just waiting for one, and we just can increase the balance between the different tasks this way and use the resources way more efficiently. How does this now look like with the tree? Because it's not just like pick a few particles, because we need the tree information as well to calculate the gravitational forces, especially on the intermediate ranges. And the tree is our main algorithm to calculate the gravitational forces. Here in this image, you can see a 2D representation of this tree. So it's a quad tree in this situation. And you have on the left the Peano-Hilbert curve, which fills this surface area. This is a 2D, and how it combines all the regions with each other. And you have the tree, which is here in this case very shallow, very symmetric, and very beautiful. And if you would now do a domain decomposition, you now also split the tree, and not just the particle information, but also the tree information. And this kind of like happens as is seen in this image here. So you split the surface area into, in this case, 4 different chunks, and each chunk then get assigned a different part of the tree. And by doing that, each chunk is not only containing the particle information, but also the tree information, which then allows a faster computation than compared to the direct summation again. But of course, this increases then, or like has the downside, of course, that you need more communications, especially at the boundaries of these areas where you needed information of the particles in the next chunk. As a summary, the code is completely OpenMP and MPI parallelized, and it scales very well on CPU only, up to, let's say, 10 to the 12 particles, which is in this weak scaling test, which we have here. So this is roughly about 300,000 CPU cores. And you can see that this works pretty well onto that kind of sizes. But as we all know, the next generation of supercomputers in the exa-scale will contain some sort of hybrid approach. So it's not CPU only, as it has been in the past, but they will use a lot of boosters or GPUs to get the computational rates they are aiming to achieve. So of course, we try to implement a way or find a way of porting parts of the code to the GPU as well. And as the tree algorithm is one of the most computationally intensive and as well as most time demanding parts of the code, we were aiming, or we already have provided or created one option, one GPU implementation of this tree already. And here in this image, just to show you a little bit how this tree building, a tree walk especially here works. On the left, you have kind of like a scheme, how a global time step for the code is supposed to work and how it looks like. And so in each time step, you do the gravity, you do all the extra physics as well, you calculate all the things. And the tree walk is very important for a lot of them. So especially, of course, for gravity, because you need to find your neighbor particles, the ones with, you calculate the gravity. But this is also important for a bunch of other processes as well. So the tree walk usually works in a certain manner. At first, you have a particle and you try to find all the neighbors. So you find all the neighbors in memory and you compute your contributions of your neighboring particles on your target particle. In the meantime, also you create like a list where you decide, where you say which information is still missing. So where are particles, you need the information where they are and all these kind of things, but which are currently not, you don't have them in memory. After this is done, you communicate this list with all the other MPI tasks, and you exchange the information so that they tell you what they need and so on and so forth. Then when you get your information, you again look, find all the neighbors, calculate the local contributions, and hopefully you have all the neighbors you need, all the information you need, and then you're done, essentially. And then you can update all the forces and everything on your particle. And this is done in parallel on all different tasks for all different particles at each time step. So what did we do? How do we port this to the GPU? What we did is there's one part which is computationally heavy. There's a lot of communication going on, but one part which is only computing, and this is what we ported to the GPU. And that's the computation of the local contributions for each particle. So we find the neighbors still on the CPU. When we have a list of neighbors, we move this to the GPU. The GPU calculates all the forces for us and sends the information back. And we do this at all steps when this computation is necessary. And this very simple approach already gives us a very nice speed up on the GPU. So here in this case, for the tree walk, you get up to a factor of 10 in speed up just by using this kind of approach for the tree walk. And this is already quite, I would say, a very, very good first step and a very good first result. Unfortunately, this isn't true during the whole computation. As I mentioned before, the universe changes its shape quite significantly during its time. So in the beginning, it's very homogeneous, which means you have a very shallow tree, very homogeneous area. And there you get these speedups of a factor 10 and even more. Unfortunately, at the end of modern time, today's time, the universe is very clustered. So the tree becomes very deep and very, it's not symmetric anymore. So it becomes really changes its shape quite significantly. And unfortunately, during cosmic time as well, also our speed up is unfortunately reduced. So it changes quite rapidly after the first clusters and first objects kind of like form. And it ends up that we have only we end up with a speed up of a factor about 4-ish. And if you look at the tree itself, or factor 2 to 3 if you look at the complete code. But keep in mind that only the tree is on GPU at the moment, so everything else is the same. But this already tells you that a speed up in the tree of factor 4 increases the code by a factor of 2. So just to give you an impression of how important the tree is within the code. So yeah, we definitely need to find a way to improve the scaling a bit further in the future. So nevertheless, with this kind of module implementation, we already we did a small scaling test just to see how it works. And we used a bunch we used the Leonardo system to do so. And in total had a bunch, 16,000 node hours. So we used 250,000 core hours on the GPU nodes and 100,000 on the CPU nodes. And even though we didn't run any complete simulations, just a few time steps actually to do the benchmarking, you already realize that just doing these tests is really expensive. And we're not talking about running the full simulations, which would require 1 million of node hours. Already scaling tests are really time demanding and require a lot of resources to execute and just to learn how things go before you can then improve them. So these are the results for the strong scaling using our GPU implementation. This is now gravity only, so we removed all the other hydrodynamics and all the other physics of the code. And you can see the scaling works quite well, actually, already. So we were so in these kind of 3 plots, you see 3 different boxes, so 3 times 3 different number of particles, so 1,024 cubed up to 4,096 cubed particles. And you can see how it scales quite nicely up to a factor of like 16 to 20-ish. But then you see a kind of like drop off. And yeah, the last test, unfortunately, at the largest number of nodes didn't work as well as planned due to time constraints. So even though we have this not perfect implementation, it scales very well. And that is already very, it tells us that we are heading in the right direction. So yeah, I will skip that due to time constraints. So what are our aims for the future? There are two main aspects we want to look at. So the first one is improving the tree. So improving gravity calculation, because the Spartan Hut algorithm is very inefficient on modern architectures, because you have this very, the leaves being single particles, and you have a lot of communication going on. And this is just not how we want to use GPUs. We don't want them to communicate. We want them to do work. So our aim is that we group particles. So instead of having a single particle per leaf, that we have a number of particles within a certain radius, and then calculate the forces via direct summation for all of these particles on the GPU, because that's what they are there for. That's what their big advantage is. And this way we can avoid this tree walk in this region. So we avoid this time-consuming and potentially computation-heavy tree walk up to a certain radius. And this is going to save us a lot of time. And also what this is a benefit then as a second step when we figured out this works is that we can then also reduce the tree time for building the tree, because if we don't need to go until the leaves being a single particle, but maybe ending that the leaf is now a number of particles, we save a few steps there as well, which then gives us also some time benefits on building side of the tree and not just on the execution. And yes, our aim is that we have a prototype within the next month, which we then can test and see and play with and see how well it performs compared to the old implementation. The next step is the data layout. As I said, the code contains a large number of particles. And in theory, each particle needs information about all the others all the time. And so there are several physical quantities attached to each of these particles, which then unfortunately ends up that we have that these structures for these particles are relatively large, so between 100 and 300 bytes. The advantage, of course, on the other hand, is it's very easy to access the quantities for each particle, because you have access to the structures all the time. And it also makes it very easy to share the information between the different MPI tasks. So that's also that's the benefit, and that's where it's coming from. The disadvantage is that, of course, large structures break the data locality on GPUs and CPU caches. That's unfortunately, you can't send these large number of data to each CPU all the time. It will just, it's simply not possible, and it will also cause a lot of memory jumps and also hamper or prevent the automatic vectorization by the compiler. So our aim is to redesign the data structures so that variables which are used together are also grouped together, and so they are closer in memory. And this way we also aim to obtain smaller data structures for the GPU offloading, because this makes our life simply much easier. So we already did some tests on that, a very simple like mini app, and just to see how this scales, how this improves the vectorization with our old implementation, so our array of structures, the vectorization was really low. And if you just split this large structure into a lot of smaller structures, we already get a vectorization percentage of like 85%. And if we then, of course, improve this even more, go to a structure of arrays, but of course, this needs a lot of careful design, we can even increase the vectorization rate to 95%. So this is definitely something where we are going to, we are able to achieve a lot of benefits with that kind of approach. So yes, thanks a lot for your attention. I hope this was interesting. And I was very happy to give you a quick introduction into the main algorithm, let's say, in the main of OpenGadget. And please feel free to ask me any questions which you might have, which you have now. So thanks a lot.
So thank you very much, Geray, for the nice presentation. And please, the questions. There is a question in the chat. What is the latest source code of OpenGadget 3 available?
So that's unfortunately one of the things we're still working on. So the code wasn't released so far, but we aim to do that until the end of the year. So stay tuned. We also aiming to write a code release paper with that, which we then can find on arXiv also. So, and then it's freely available for everyone to use to their liking. So a few more months and then it will be there.
Thank you.
So hello, am I audible?
Hey,
Yes.
I can hear you.
Yeah, so I had one question that, yeah, so hello, yeah. So as you rightly mentioned, first of all, thank you for the talk. And so as you rightly went through it, that communication latency and all is like not that big a issue on the present scale. So what is the need for the exascale computing as for your only for your application per se? If you're not getting too much of latency in communication.
Okay, so if I understand your question correctly, you're asking
Yeah.
us why we want to go exascale in general, right? Or
Yes, sure. I
yeah,
mean,
so
in general,
yeah.
I know because
Mhm.
I'm working on another application as well. But in your application, I don't see like actually. But could you please showcase again, like where exactly is the communication head that you would need more advanced exascale computing? So that is one my question is.
So yeah, so of course we want to reduce the computational overhead. That's for sure, because you know, computational time is not unlimited, and as we want to run larger simulations in the future with better physics, and that will mean that we have to solve more equations at the same time, and that's what we will need exascale for at the end of the day, because otherwise it's simply not possible to run the next generation of simulations which can cover the largest to the smallest scales. So, and yeah, to do so, of
Sure.
course,
So
we need to improve.
if I understand correctly, so you showed like you were trying to do it until 10 raised to 12 particles, if I'm not wrong. So right, there was
So
a scale of 10 raised to 12.
yeah,
It was like
that's the current scaling, yes, on
yeah
CPU only, what we tested so far. Yeah.
on CPUs. Okay. Yeah.
Mhm. Yeah, and we want to increase that simply because currently we are limited by like a particle mass is roughly of the order 10 to the 4 solar masses, would say roughly. It's not the limit, because then our subgrid physics kind of like will break more or less. And of course, by implementing better models, we are able to reduce the particle mass and therefore have higher resolution, and therefore are able also to show and, you know, trace better the physics which are involved in this, all these processes which are forming galaxies, and that we can do that in more detail, get more insights. So at the end, we will need more particles.
Yeah, sure. All right.
Are there any more questions? If not, then I will thank you for participating, and especially thanks to Geray and Luca for preparing this presentation. And there will be one more space COE presentation. In July, we will have the presentation of Changa code and the Charm framework. So you are cordially invited to attend also this training. The registration is available on the Space COE website. So please head there if you would like to continue with us with the space series of introduction of the codes that we are working on. So thank you very much, and I hope to see you at our next trainings.